Today we will be talking of the perspective projection, and then if time permits we will go on to hidden surface removal. In a perspective projection, the basic idea is that when we are looking at any object, we want to draw the object the way our eye sees it. Okay, that means if we have a cube and we want to draw a orthographic view from that is the front view, let's say, we will just get a rectangle. Okay, but when we draw the perspective view, we won't get a rectangle because our eye is located at a particular point, and since our eye is located at a point, our view is going to be different. Okay, we will be able to see the side edges also. Okay, the side faces, that is. So our view might look something like this. Okay, this is basically because the projecting lines from the object are not parallel. The projecting lines are going to be all focused at the eye. Okay, for example, if you have any point here x, y, z, these are coordinate axis x, y, z, and this is the location of the eye. This is going to be the projecting line. Okay, so if this is the eye, all the lines are going to be projected in this manner. Okay, earlier when you are talking of the orthographic projection, the projecting lines were all going parallel. Okay, and we had a projecting plane like this. Okay, so this is the projecting plane, and the projecting line, instead of being parallel, are focused on the eye. In that case, a point here will get transformed to this point will get transformed here, and this one will get transformed here, and so on. Okay, so in the case of a perspective projection, we always define the location of the eye and we define a projecting plane. In this particular figure, I have taken the projecting plane to be the xy plane. Okay, the projecting plane is this xy plane, that is the plane where z is equal to 0, and the eye, instead of being located at infinity, is located at the coordinates 0, 0, minus d, where d is this distance from the origin to this point. I am assuming that the eye is right now located in the minus z direction. Okay, the projecting plane is the xy plane, and we want to project any arbitrary point xyz onto this projecting plane. Okay, so this arbitrary point xyz will get transformed to a point x prime, y prime, z prime, which will be on the xy plane. So obviously z prime will be equal to 0. Okay, so this way if you have a set of points, they will all get transformed such that if I join that point xyz to this eye, to the location of the eye, the intersection of this line with the xy plane is going to give us the transformed point. Okay, in the earlier case, the point xyz, when projected onto the xy plane using orthographic transformation, was just getting transformed to xy. Okay, the x and the y coordinate won't change because our projecting lines were earlier parallel and perpendicular to the projecting plane. In this case, all the projecting points are going to make a different angle to the projecting plane. Okay, how do we find the coordinates of this point x prime, y prime, z prime? From this point P, I have drawn a perpendicular onto the xz plane. Okay, this vertical distance will be equal to y. Okay, similarly from this point if I draw a line parallel to the x axis, this distance will be equal to x. That is because of the coordinates of this point. Okay, and from this point to the origin, this distance is going to be equal to z. You are all right? Now this is the origin. Let's say this is the IE. Let's say this is my point A, this is B, let's say this is C. Okay. Now in this figure, let's consider triangles EC P prime and triangles and EAP, ECP prime and EAP. Okay, that is the ICP prime and EAP. Okay, if you look at these two triangles, this distance from C to P prime, this is the y coordinate of the point P prime. Okay, so this distance will be equal to y prime. Okay, so from these two triangles, we can say EC divided by EA would be equal to CP prime divided by AP. Okay, which would be equal to CP prime is y prime, AP is y. Okay, I can put both of them together. Can you see it clearly? Both the figure and the text. Okay, so EC by EA, that is this distance divided by this distance, would be equal to y prime divided by y. Okay, now let's consider triangles ECO and EAB. Now we can say EC divided by EA will be equal to CO divided by AB, and it will also be equal to EO divided by EB. Okay, so CO divided by AB, that is CO is nothing but x prime. So CO is x prime divided by AB, AB is x. Okay, this is equal to EO. How much is EO? D. EO is the distance of the eye from the projecting plane. So D divided by EB. Okay, now EB is going to be equal to EO plus OB, which is equal to D divided by D plus Z. Is that alright? And we know that Z prime is equal to 0. Okay, now let's look at these equations. From this and this, we will get x prime is equal to x multiplied by d divided by z plus d. Okay, which I can write as x divided by 1 plus z by d. Okay, just divided d in the both in the just divided by d both in the numerator and denominator. Okay, so this is one equation. Similarly, if I take this equation, EC by EA, I can take from this equation, EC by EA is equal to this figure. So y prime by y is also equal to d divided by d plus z, or is equal to 1 over 1 plus z by d. Okay, and this implies y prime is equal to y divided by 1 plus z over d. Okay, so this is the second equation. Is that all right? So now we have got the x prime, that is the x coordinate, we have got y prime, and we know that z prime is equal to 0. So if you take these three equations, we will get x prime is equal to x divided by 1 plus z over d, y prime is equal to y divided by 1 plus z over d, and z prime is equal to 0. Okay. Now the first thing to be noticed is that these transformations, they are non-linear transformations. Okay. All the transformations that we saw earlier, that is, we had seen translation, we have seen rotation, and we have seen scaling and orthographic projections. Okay, and orthographic projections. All these were linear. Okay, for instance, translation, that was captured by just a simple addition of a translation vector. Okay, rotation, that was captured by a matrix which was something like cos theta, sin theta, 0 0, minus sin theta, cos theta, 0 0, 0 0, 1 0. Okay, in this the value of x prime is x cos theta minus y sin theta, that is a linear combination of x and y. Similarly, the value of y prime was x sin theta plus y cos theta, that is again a linear combination of x and y. Okay, z prime in this case was equal to z. Okay, so all x prime, y prime and z prime were linear combinations of x, y and z. Okay, but this is not a linear combination of x, y and z. Okay, x prime is equal to x divided by a term involving z. Okay, that means x prime is not a linear combination of x, y, z. Similarly, y prime is also not a linear combination. That is why these kind of transformations come under the category of non-linear transformations. Okay, and if we want to write them in the form of a normal transformation matrix, the way we have been doing so far, what we will have to do is x prime, y prime, z prime h, we will have to use the homogeneous coordinate Now both x prime and y prime are being divided by the term 1 plus z by d. Okay, so what we will do is we will get h equal to 1 plus z by d. For getting h to be 1 plus z by d, in the last column we will say 0, 0, 1 by d, 1. Okay, so that this row vector multiplied by this column will give us the term of 1 plus z by d. Okay, this way 1 plus z by d will be the value of h. Okay, if h is equal to 1 plus z by d, effectively x prime, y prime as well as z prime will get divided by the same number. Okay, and x and y will retain as the same values. Okay, this way by having a 1 by d term here, we will get the homogeneous coordinate to be equal to 1 plus z by d, and effectively both x prime and y prime will be x divided by 1 plus z by d. Okay, if you look at this, we will get x prime equal to x, y prime equal to y, z prime equal to 0, and h equal to 1 plus z by d. Okay, so this point would be the same as the point x divided by 1 plus z by d, y divided by 1 plus z by d, 0 and 1. Okay, so this way we will be able to capture this nonlinear transformation. Is that all right? So capturing this perspective transformation, we put a 1 by d term in the fourth column. Okay, and then if we now look at our general 4 by 4 matrix which we have been using for transformation, we said this term will be used for uniform scaling. Okay, these three terms are being used for translation. Okay, these 9 terms are being used for different rotations. Okay, then these terms, the diagonal terms, we are using for scaling, and now we have seen that these terms would be used for the perspective transformation. Okay, so these three terms are non-zero at any point. We can know for sure that there is some perspective transformation involved in it, or some nonlinear transformation involved. By using these three terms, we are able to get nonlinear transformations. Okay, if you remember when we were talking of homogeneous coordinates, we had said that the homogeneous coordinates will help us capture different types of transformations. By getting a different value of h, we managed to capture perspective transformation using ordinary transformation matrix. Okay, by using these positions, we can capture nonlinear transformations which involve the term of x, y and z in the homogeneous coordinate. Okay, right now we are getting only one term over here. If you want to get or rather in which under what circumstances will these two terms be non-zero? Anyone?
X or y axis.
What is that again?
When the I is along the x or y axis.
When the I is along the x or y axis. Right now we have taken the I to be along the minus z direction. Okay, if the I is in the minus x direction or in the minus y direction, okay, in that case we will get non-zero terms in these two positions. Okay, if our I is in the minus x direction, then we will get a 1 by d term over here. Okay, similarly if our I is in the minus y direction, we will get a 1 by d term here, and so on. Okay, so this is how we capture the perspective projection in general. Any questions on the perspective projection? Okay. Then let's talk of the perspective projection when the eye is at the origin. Okay, and the projecting plane passes through the point x naught, y naught, z naught and has a unit normal vector given by L, M, N. Okay. If this is a projecting plane and the eye is at the origin, in that case how do we get the perspective transformation? This is our projecting plane and this is the location of the eye, that is at the origin. Okay, and now we want to find out the transformation matrix for this case. Okay, any suggestions on how to find the transformation matrix?
Must we rotate the plane so that it rotate the origin so that the plane is along the axis?
We rotate the origin. What do you mean rotate the origin?
Rotate the coordinate system.
Okay, so we rotate the coordinate system so that
The plane is along one of the plane is one of the principal planes.
Element points to
Either
0 to 1.
XY plane or
just by rotating the
rotate
plane.
and then translate.
So we rotate and then translate so that this plane, this projecting plane becomes one of the principal planes. Okay, that can be one way of doing it. Okay, but there is a much simpler way of doing that. See, what you are saying is that we will translate this point, let's say, to this point. Okay, or alternatively, from this point we will draw a unit normal, or sorry, we will draw a normal onto the plane. We will translate this origin to this point and rotate the axis so that one of the principal axis points in the direction of the element vector. Okay, and then we can use the transformation matrix which we found in the previous step. Okay, but that is going to be a very complex procedure. Instead of that, we can again use our equations from geometry. Okay, if we have any arbitrary point, here that is the point x, y, z. If this point is transformed onto this plane, that will be the intersection of this point with this line. Okay, let's say the intersection is somewhere here, that is my point P prime. This is my point P. Okay, now this point P prime will satisfy the equation of this plane. Okay, and if this point P prime is satisfying the equation of this plane, what is the equation that we will get for this point? What will be the equation for this plane?
The dot product of the two vectors.
The dot product of this vector with this unit normal vector has to be equal to 0. Is that okay? Let's say this is my vector, let's call it V. So the vector V dot with L M N has to be equal to 0. This is because this vector V is a vector in the plane, and this vector Lmn is a normal vector to the plane. Okay, so Lmn has to be perpendicular to every vector in the plane. Okay, and if two vectors are perpendicular, their dot product has to be 0. Okay, so the dot product of V with Lmn will be equal to 0. We say V dot Lmn is 0. And what is this vector V? Vector V will be x prime minus x, y prime minus y, sorry, x prime minus x naught, y prime minus y naught, z prime minus z naught. Okay. So if we consider this vector V and its dot product with Lmn, that has to be equal to 0. That means x minus x prime minus x naught, y prime minus y naught, z prime minus z naught dot with Lmn is equal to 0. That will mean L times x prime minus x naught plus m times y prime minus y naught plus n times z prime minus z naught will be equal to 0. Okay. The other thing that we have to notice is that if we have this point P and we are joining it to the origin, what is the equation of this straight line? What will be the equation of this straight line?
X prime lying on that line. X prime divided by x is
Yeah.
equal to y prime divided by y is equal to z prime divided by.
Okay, so if we take any point on this line which is given by, let's say, x prime, y prime, z prime. Okay, then x prime by x will be equal to y prime by y will be equal to z prime by z. Okay, or we can say x prime will be equal to t times x, y prime will be equal to t times y, and z prime will be equal to t times z. That's all right. Okay, essentially if we have any 2 points x1 y1 z1 and x2 y2 z2, and we want to find out the location of any point xyz on this, we can write down the parametric equation of this line. Okay, using vector notation, let's say if this point is P, we can say that P will be equal to x1 y1 z1 plus, let's call this P1, let's call this P2. Okay, plus we'll say P2 minus P1 times T. Okay, or we can say it is P1 plus P2 minus P1 times T. Okay, any point P on this can be given by this relation. The same thing we are doing over here. A point P1 is a point 0 0 0 and a point P2 is a point xyz. Okay, so we are getting the point P, which is x prime, y prime, z prime, and the point P2, which in our case is xyz. So x prime, y prime, z prime, P1 is 0, so this will be equal to x, y, z times t. Okay, so from this we will get these three relations. X prime will be equal to t times x, y prime will be equal to t times y, and z prime is equal to t times z. Okay, now if you look at this relation, okay, we need to get the value of x prime, y prime, z prime, which is the intersection of this line with this plane. So both these equations have to be satisfied. Let's say this is equation A and this set of equations is equation B. So the value of x prime, y prime and z prime will put into this equation. Okay, if we do that, what we will get is L times Tx minus x naught plus m times Ty minus y naught plus n times Tz minus z naught will be equal to 0. I have taken this equation and these equations and I have got this. Okay. So I have put x prime over here, y prime over here and z prime over here. I will get this equation. Okay. So now if I find out the value of t from this equation, I will get t, or let's do it step by step, t into Lx plus my plus nz minus Lx naught minus my naught minus nz naught is equal to 0. Okay, this term is coming here, this term is coming here, this term is coming here, and this term is coming here, this is coming here, and this is coming here. Okay, so from this I will get t is equal to Lx naught plus my naught plus nz naught divided by Lx plus my plus nz. Okay, and our projection point in this figure, this point P prime is given by x prime is equal to t times x, y prime is equal to t times y, and z prime is equal to t times z. Okay, where t is given by this relation. Okay, so this is how we will get the perspective projection in this case, where the eye is at the origin and our projecting plane is any arbitrary plane. Okay, this is my point P, this is my point P prime. The point P prime will be given by these relationships. Okay. Now in this, if you look at Lx naught plus my naught plus nz naught, what does this correspond to?
Distance from origin.
Again,
Distance of the plane from origin.
distance of this plane from the origin. Lx naught plus my naught plus nz naught is the perpendicular distance of the origin from this plane. Is that alright? Okay, so this we will say is equal to d divided by Lx plus my plus nz, where d is the perpendicular distance of this plane from the origin. Okay, and if you want to write this relationship using matrix multiplication transformations, how do we do that? We have to say x prime, y prime, z prime, h. X prime is t times x, but t is given by this. Okay, and again Lx plus my plus nz is coming in the denominator. Okay, so this is also a non-linear transformation. Okay, because Lx plus my plus nz is in the denominator. I can put these terms here. This is equal to d times t divided by Lx plus my plus nz. This will be equal to d times t divided by the same term. This is also equal to
D times x.
sorry. Sorry. So this is equal to d times x divided by this term. Y prime is equal to d times y divided by this term, and z prime is equal to d times z divided by this term. Okay. So again we'll take this complete term into the homogeneous coordinate. To get this complete term in the homogeneous coordinate, we'll say L M N 0. XYZ1 when multiplied by this vector LMN 0 will give us the term Lx plus My plus Nz. Okay, and here we'll just say D 0 0 0 D 0 0 0 D 0 0 0. Okay, this set of equations will give us x prime will be equal to x times d, y prime will be equal to y times d, z prime will be equal to z times d. Okay, and h will be equal to Lx plus My plus Nz. So this point will be the same as the point xd divided by this term, yd divided by this term, and zd divided by this term. Okay, this term is Lx plus My plus Nz. Okay, similarly you get that here also. Okay, so this would be this point, which is the perspective projection of the point P. Okay, that is what we have got over here. Okay, any questions on how we have got this perspective projection? Any question on this? Okay, so if the eye is at the origin, okay, I'm coming back to this figure. If the eye is at this origin, the projecting plane is any arbitrary plane. Okay, in that case, we can project a point P onto this projecting plane using this set of equations. Okay, so now in perspective projection, let's see one more thing, and that is a general perspective transformation. Okay, in this case, we say that the eye is at any arbitrary point A, B, C. Okay, so if I draw my this is my origin. So my eye is located at any arbitrary location. Okay, which is given by the point A, B, C. Okay, and the projecting plane, this passes through some arbitrary point x naught, y naught, z naught. okay, and has unit normal vector of L M N. That means the projecting plane is any arbitrary plane like this. In such a case, if you want to take any point and transform it on and get the perspective projection of that, how do we do that? In the last case that we had, the projecting plane was the same as this, but the eye, instead of being at ABC, was at the origin. Okay. Now what I am saying is that eye is also at any arbitrary location, the plane is also any arbitrary plane. How do we get the perspective projection? Now in this case we will use a standard projections. Okay. The first thing that we will do is step 1, we will translate such that I becomes at origin. Okay, and that is translation by minus A, minus B and minus C. Okay. The step 2 would be the general perspective projection that we have seen. Okay, and this projection is given by this vector. Okay, and then in step 3 we will just do the reverse of 1. Okay, which is translate by A, B, C. Okay, and then the combination of these three will give us the general perspective transformation. Okay. Any question up to this point? Okay, just one more thing in perspective projections, and that is the concept of what we call as vanishing points. You know what is a vanishing point in a perspective projection? Anyone?
One behind the other.
One behind the other?
In the line of
No, no. You don't know what are vanishing points? Okay. I think in that case what I will do, I will define the vanishing points, and how to get the vanishing point that we will briefly see in the next class. See, vanishing points, if you have a set of parallel lines, okay, that means let's say if I want to draw a cube, now this, in this case I am taking the projecting plane to be parallel to the front face of the cube. Okay. So if you remember in one of the earlier classes I had given an example of the railway track. If you are standing in the middle of the railway track, you look at the distance, you will get a view something like this. Okay, these two lines will seem to come from this point. Okay, which is actually a point at infinity, but when you project it onto a vertical plane, this will be a finite point. Okay. Similarly, in a cube, the two edges which are at the back, they will seem to come from a finite point. Okay. So let's say if this is my axis, my projecting plane is right now the YZ axis, and all lines parallel to the X axis will seem to come from this point. Okay, so the view of the cube would look something like this. Excuse me. Okay, because the lines which are parallel to the x axis would seem to emerge from this point, which is our vanishing point. Okay, so vanishing point is a point where all lines, all parallel or a set of parallel lines will seem to come from. Okay, in this case, since my projecting plane is parallel to the yz plane, lines in the y direction will continue to remain parallel. Lines in the z direction will also continue to remain parallel. Okay, two parallel lines in the z direction, in the y direction or in the z direction, they will always be parallel. Okay, but two parallel lines in the x direction will seem to come from a point which will be a finite distance away. Okay, so this is one vanishing point. Okay. Similarly, if my plane is at a slight angle, okay, then possibly you might have a situation like this. In this case, all my lines parallel to the y direction seem to come from this point. All the lines parallel to the x direction seem to come from this point, and all the lines parallel to the z direction continue to be parallel. Okay, so here we have got two vanishing points. This is vanishing point 1 and this is my vanishing point 2. This vanishing point corresponds to line in parallel in the x direction. This one corresponds to lines parallel to the y direction. And for lines parallel to the z direction, they will continue to be parallel. So this is the case where we have one vanishing point. Here we have got two vanishing points. Similarly, we can also have three vanishing points. Okay, that means lines parallel to the z direction, they will also seem to emerge from a finite point. Okay, now these vanishing points correspond to lines parallel either to the x direction or to the y direction or to the z direction. Okay, so these are called principal vanishing points. Okay, if we have a set of lines which are, let's say, in the direction given by the vector 1 1 0, okay, which is a vector like this. All lines parallel to this axis will also seem to come from some other point. That will also be a vanishing point, but that will not be a principal vanishing point. A principal vanishing point is a vanishing point corresponding to the three principal axes. Okay, a vanishing point is defined as any point or a point from where a set of parallel lines would seem to emerge in a perspective transformation. Okay, the set of lines may or may not be parallel to the principal axis, but in the principal vanishing points, the set of lines have to be parallel to one of the principal axes. Okay, so this is how we define vanishing points. For the general perspective transformation, How do we find out vanishing points? We'll briefly see that method next time, and then we'll go on to the next topic, that is hidden surface removal. Okay, that's all for today.